Great, let's get started. Hi, everybody. Let's welcome you all to the Carbon Capture Innovation Challenge organized jointly by Extreme Tech Challenge and SOSV. A little bit about us. Extreme Tech Challenge, or XTC, is the world's largest startup community for tech innovations that truly build a better world. It was founded 10 years ago. Fast forward today, we're now the world's largest marketplace for innovation, attracting over 5,000 startup companies from over 120 countries that enter our competitions and events across the world. And we're very unique in a way that we cover every tech vertical that you can think of, and very inclusive of startups from various funding stages, because we really believe that innovation has no border and diversity truly strengthens the innovation ecosystem. And our mission is to find the most promising companies that are building a better world, and then give them what we call rocket fuel to take them to the next level, which include global visibility, access to VC funding, corporate strategic partnerships, and mentorship. And we do this by partnering with over 20 large tech conferences globally, including this one, as well as holding our own summits and events, including monthly networking dinners from all over the globe. And this model is working. We've seen that recent XTC cohorts have raised over $4 billion in VC funding, and we've seen over a dozen companies exited. So I think this really is a testament to the power of our investor community to not only identify the companies that have massive scaling potential, but also providing them the resources and the networks to help them scale their innovations. And today we're just super excited to be joining hands with our friends and colleagues at SOSV to recognize the founders that are really pushing the boundaries of carbon capture and removal technologies. Because we believe by bringing our communities together at this event, attended by over 5,000 investors, founders, technologists, and domain experts, we really look forward to fostering these meaningful engagements and connections between investors and entrepreneurs to celebrate these scalable innovations poised to make a big impact. Because that's really the magic of XTC. So today you're going to hear from the top 5 companies innovating in this area. Each of them going to pitch for 3 minutes, followed by 5 minutes with judges on Q&A. First, before I get started, I'd like to just thank and recognize all the founders that have entered the competition, and also the evaluators that have devoted their time and expertise during the earlier evaluation rounds to help us identify the most promising companies. And then now it's my pleasure to introduce 3 judges for our session today. Bill Tai, who is the co-founder of Extreme Tech Challenge, partner Emeritus at CRV, and one of the most successful early stage investors in the world, himself having been entrepreneur and a corporate innovation executive as well. And then second, let's welcome Andrew Gollach, principal at SOSV Hacks. And then let's welcome Sophie Purdom, managing partner at Planeteer Capital and co-founder of Climate Tech VC. So welcome, judges. Look forward to a really engaging session. Now, we're going to introduce the first company presenting today, Carbix, who is a developer of advanced weathering technologies designed to transform carbon dioxide into building materials. Carbix, you have the floor.
All right. Hi, I'm Quincy Sammy. I'm the founder and CEO at Carbix. And Carbix is capturing CO2 emissions and transforming them into advanced building materials for the global construction industry. The problem that we're addressing is industrial carbon capture and utilization from point sources as well as natural gas plants. The current technology suite in this emerging sector is still evolving, but are often inefficient, costly, and represent a large cost burden for hard-to-abate industries. Our technology avoids these issues. We capture CO2 and generate product on site. Our technology is a photobioreactor that's designed to fast batch CO2 into products within minutes and seconds through a pathway called mineralization. Nature can perform the same function, but it usually takes thousands of years. The global market opportunity is $1 trillion building materials, and construction sector. Our go-to and beachhead markets are cement and concrete. We like this space because concrete's the second most used product in the world and a durable sink for CO2. Over the last year and a half, we've been fortunate to form partnerships with industry like Saint-Gobain, where we're currently planning our first commercial pilot. And supporting that scale up is the Massachusetts Clean Energy Center. We conducted a study of a float glass facility owned by Saint-Gobain in Europe. And this is an example of the multiple revenue streams that we can generate. As you can see, high purity carbonates are the most price elastic. The key takeaway from the study was that we can operate for under $50 a ton, and our impact with just 10 sites like these would be capture and avoidance of nearly 3.3 million metric tons of CO2. We produce three primary products: 2 cement blends, which can be used to develop aggregate, and also high purity carbonates. And this is a team that's responsible for our past development success and our future commercial pilot success. Myself, I have over 12 years in clean tech design engineering, and I'm supported by my co-founder and CSO, Vinit Deej, a PhD in aerodynamics. And we're both supported by 2 amazing advisors, both PhDs in their respective fields. Over the next year and a half, we plan on completing product certification of our concrete cement blends, as well as initiating our first commercial pilot in northern Massachusetts. The way that cement and concrete is made today is simply not sustainable. We believe that the gold standard for future clean cement and concrete will involve carbon capture and use and our technology. Join us as a partner in this opportunity in creating a carbon neutral and potentially carbon negative future. Thank you.
Thank you, Johan. I'm going to turn to the judges for your questions.
I have a question Bill Ty asking. I have companies like this over the years, several times over the decades, actually. What makes the timing right for this now? And have there been any changes in either chemistry or cost structure or process that make this more viable economically now than before?
So I think our technology is really what we're depending on to speed up the reactions and also create product in a fast batch, and that's in sync with commercial facilities, their exhaust throughput, essentially. Most of mineralization is an old technology. We do use a wide blend of waste and fresh minerals. And I think the timing, a couple of things are helping us in terms of timing. It's a huge focus on decarbonization and building materials. Carbon taxes are in play, especially in New York and in some parts of Europe. And so that's driving forward. But I think more importantly, corporate and industry partners are really facing mandates, not only from their shareholders, but local communities to really cut down on building emissions. And one way to do that without having to reinvent anything is to change processes, which is carbon capture.
Building off of Bill's question, this is Sophie Purdom from Planeteer. Tell us more about your source of the feedstock, of the CO2 feedstock. Where are you getting it from? Are you developing this? Are you doing this kind of sequestration in situ? Do you have to store and therefore pressurize that CO2 feedstock? How clean does it need to be? All of those important pieces, please.
Sure. So we're currently our first pilot's about 30,000 metric tons, and it comes from natural gas and also kilns and furnaces. So the concentration in the CO2 stream can vary anywhere between 5 to 20%, depending on the load on the gas turbine. So we are direct injecting CO2 under pressure, and we use a combination of high and low speed mixing, UVC dosing of water inputs, a varying CO2 partial pressure up to 400 psi, as well as, and finally, energy recovery with thermoelectric generators. So the end process is a fast batch of CO2. We release the nitrogen stream, which is the biggest constituent of any exhaust stream, as well as some oxygen. And when we return, once the carbonation process, or we pull the CO2 into the mineral and create the carbonate, the remaining gases are reintroduced into the exhaust flow.
Would you say that the core differentiator for your technology is your injection capabilities, or piecing together all of these different process steps?
So I think our reactor technology stands out, the way that we're able to fast match, and also by using mineralization, we can avoid some of the more costly steps like CO2, concentrating CO2, and some other, which has really been the industry standard, like using amines. So we're avoiding that and going through direct injection, so that really drops a big expense out of our process.
We have time for one more question.
Yeah, can you tell me a little bit about your unit economics here? So I think I caught your sequestering at about $50 a ton.
Right.
What does that translate into in terms of like sales of product that you're getting out of the system?
Right. So that was based on a flow glass facility in Europe. So the products that we're really looking to pull out are carbonate cements. We produce another type of cement called mafic cement. But the primary product always coming out is going to be a carbonate, no matter where it comes from, whether it be from blastonite, gypsum, or other type of waste materials like lime kiln dust, cement kiln dust, or even rice husks and recycled concrete. So in keeping the product itself, we're fairly competitive with current cement blends. So we're pricing at around 125 to 130 a ton. For our cements, aggregates around 20 a ton. Most of aggregate production is automated. We use 3D printing, also molds to produce them on a mass batch. The high purity carbonates are elastic, so they can be applied to different industrial functions. And so those, in terms of pricing, high purity carbonates range from anywhere from 310 upwards to 700 per ton. And lastly, although we're not dependent on incentives, they're great to have, and they definitely help out the first year, especially our ramp up here. So incentives for like the 45Q will generate about $65 per ton of CO2 captured, and that's a net number. So we do have to include our CO2 inputs, and then other like the EU ETS scheme are a bit higher at 90 to 100 per ton, but they are cyclical, so the prices change.
Great. Thank you. Thank you, Johan from Carbix.
Thank you.
Let's give the judges a few moments to enter your scores while we ask for Carbonautan to stand by to take the stage. Okay, I think the judges are almost ready. Another 10 seconds. Okay, the floor is yours.
Can you see my screen?
We see infinities of your screen.
Oh, this doesn't work. I have a problem. Can I share my screen? I have the problem. I'm now in Firefox, but the slides are in Google.
Should have used Zoom.
Sorry?
Great, help is on the way.
Yeah, share the tab and then go to the tab.
They got a good deal on Hopin, but Zoom just works.
Just share the correct tab. If you share it and then share what you're looking at, you're infinitying it.
So I don't share the screen.
You were doing the right thing. Then you have to go to the tab you're sharing.
Yeah, to Google Chrome. I'm now in Google Chrome.
Okay.
Stefan, should we go on to the next presenter and come back?
Yeah. We'll come back to it.
Okay, we'll come back to you, Torsten. Okay,
Yeah,
so let's invite Sequestrate to take the stage.
Hello.
Hang on just a second. We're waiting for Torsten to also leave the stage. Great, welcome. The floor is yours.
Thank you. I'm just about to share my screen. Can you see my slides okay? Great, thank you. Thank you for having me. We are Sequestrate. We take rocks, sequester CO2, and with it make low carbon materials. The world has a carbon storage problem. We need to remove 10 gigatons of CO2 per annum from the air by 2050. DAC companies are working to solve the air extraction part, but need help with storage. On the other hand, CO2 that could easily be captured is being freely emitted today by industry. Why is this? Because there's nowhere to permanently store it. Sequestrate is solving this storage problem. We leverage a process that naturally occurs in the Earth's carbon cycle, the weathering of rocks, which removes over a gigaton of CO2 from the atmosphere annually in a natural process. Our industrial reactor speeds this reaction up 100,000 times using a reactor designed by ex-oil and gas engineers, turning it into carbonate, which is a form of carbon that will stay out of the atmosphere for over 1,000 years. With this, we're also decarbonizing one of the hardest to abate industries in the world, construction, which accounts for 11% of all global CO2 emissions. The material resulting from our process is initially being used to make low carbon concrete blocks. However, we're also looking at supplementary cementitious materials, bricks and roof tiles, agricultural products, paints, and pigments. We're also solving problems for mining, who produce billions of tons of mine waste a year, much of which could be suitable for our process. With that in mind, our process has been designed to stabilize and reduce their mine waste while increasing monetization for them. And as a result, we've been talking with quite a few multi-billion-dollar mining companies. Our initial feedstock is olivine, but we plan to scale up with mine waste in the long term. Our process incorporates key features for successful carbon removal. We have a patent-pending reactor optimized for low energy, a closed-loop process which doesn't require any modeling or estimates for the CO2 sequestered, and the amount of feedstock we require is abundant around the world. Most of all, we scale in a modular fashion with a reactor that can be containerized and delivered around the world to wherever it's needed. Our team is myself. I was a founding member of IHS Markit, which last year sold for $43 billion, and 2 ex-oil and gas engineers, both with over 30 years experience in the oil, gas, and chemicals industry. Today, we have a partnership with the University of Nottingham, where we have a 10-ton-a-year rig with 18 months of test data, our first patent file for our energy-efficient reactor with more in the pipeline. We produced our first sample concrete blocks, and we're planning to lay our first paving stones with our university partner on site. We're also engaged with partners and local authorities for our first 1,000-ton pilot in the UK. In the long term, we will be able to sequester CO2 for $30 a ton, reduce the carbon footprint of concrete blocks by 100%, and scale to sequestering a gigaton per annum. Thank you.
Thank you, Nishal. Judges, jump right in.
Thanks so much for sharing. I heard modular in there, right? These modular reactors that can be shipped around in, container sites, for example. But then you're making things like paving stones, right? Which are heavy and probably aren't also being used on site. So tell me about, why is modular better in this use case? Why does it matter to bring the modularity to the point of sequestration when you probably are not going to be doing modular construction applications?
Sure, absolutely. So we're starting with modular because the CO2 supplies we're identifying are falling into this bucket between 10 to 50,000 tons per annum in terms of CO2. And there's many of them. We've identified 900 candidates in the UK, 9,000 in Germany, and they require a solution which is not too big. And they're falling out of they're finding themselves not eligible for the geologic sequestration pipelines that are being built. For example, there's a gigaton pipeline being planned right now in the north of England. And we spoke with quite a few CO2 producers there, and they're all out of scope for that pipeline because they're just simply not big enough. So we can create this modular reactor, ship it to wherever our CO2 partners are, and then make concrete blocks on site. Additionally, the thing about concrete is that it's a localized market. We don't want to be making it in one centralized place and then shipping it around the world. We want to be able to bring it to wherever the local markets are, and this allows us to do that.
Okay, so instead of kind of capturing and then shipping around the CO2 maybe through a tanker or something else, you're suggesting that there's stranded CO2 assets, and it makes sense to bring the sequestration to that site.
Right.
Okay.
Yeah, we want to co-locate
Thanks.
with the CO2 suppliers. Yes, absolutely.
So I apologize if I missed it. Can you walk me through exactly what it is that's coming out of the system? Is it, so I caught that you're bubbling CO2 into like mine tailings waste. Is that effectively?
Sure. Yeah, we're starting with olivine today. So I'm not sure if I actually said that, but we're starting with olivine today, partly because a lot of the mining companies, they don't actually have enough CO2 to match their feedstock at the moment. So in the long term, we're looking for DAC partners to bring that in. And as we've proven our technology, there may be scope for bringing pipelines of CO2 into the mine waste. But what we're doing today is we're taking olivine, we're injecting pressurized CO2 into the reactor. We've got a bunch of innovations to minimize the reaction cost. And what comes out of that is magnesium carbonate and precipitated silica, both of which both have been used in aggregates. Magnesium carbonate is found in dolomitic lime, and the precipitated silica is a supplementary cementitious material, which I was with a meeting at the Institute of Structural Engineers today, and they're looking at the amount of steel slag that is out there today and how it's already being tapped out. And that is the code 2 SCM right now in the UK, and they're looking for alternatives.
Yeah. So do you need to go through certifications on that SCM then?
Okay, so it's a good question. To get to scale, we do certainly need to do that. We're finding partners who are willing to take our product right now without necessarily getting certified, depending on the use case. So we look at paving stones. There's a lot less risk. There's not much structural load on that. So people are willing to go and work with us on that. As we prove out the properties and we get certifications, we are likely to be able to scale up.
We have time for one more question.
I think maybe the natural question here, how does the price point of your SCM compare to other SCMs on the market?
Sure. Steel slag today retails for slightly lower than cement, which is about 130 pounds a ton at the moment, so about 150, 160. We can make our process work at $100 a ton. At that point, we can sequester at 30. We can charge on the carbon credit side at $30 a ton.
And can you fully replace a 100% of SCM in cement, or is it a fraction?
We cannot fully replace cement, not with that current process now. We're looking to partner with companies who are, there's geopolymers, other things coming in too. But we also, because we're storing CO2 in the block via the magnesium carbonate, we are offsetting the emissions from elsewhere. And our initial target CO2 suppliers are all biogenic sources, so they will be true carbon removals.
Great. Thank you, Initial. Thank you.
Thank
you for your presentation from Sequestrate.
Bye-bye.
Great. Next, let's give judges a minute to finish your scoring. Great. Next to take the stage, let's welcome Mantle.
Hi, folks. How am I doing on screen sharing?
Looks good.
Yeah, cool. It's great to be here. My name's Cameron, and at Mantle, we're developing the material solution to carbon capture. So our technology enables the highly efficient removal of CO2 at the source, so point source carbon capture, in a manner that cuts the cost of decarbonizing these hard-to-abate industries by half. So we need to be capturing billions of tons of CO2 from these industries, including industrial heat, cement, steel. And also by removing CO2 from the air, we can pair point source carbon capture with biogenic sources of carbon. And all of this captured CO2 needs to be transported and either utilized or sequestered. But the driver of cost is typically the capture step. And we believe that the lowest cost capture technology will dominate this soon-to-be trillion-dollar industry. So at Mantle, we've developed the first high-temperature liquid phase carbon capture materials. by doing carbon capture at a high temperature, we can do it extremely efficiently and solve the challenges with the existing amine technology, which is its energy intensity. It's a little counterintuitive, but by doing carbon capture at a high temperature, we recover high-grade heat from the absorption process in a manner that offsets the heat required for desorption. And by using liquid phase chemistries, we can do that in a way without material degradation or decay and scale this technology to the scales needed to meet the demand. What that means in practice is we're able to cut the cost of carbon capture relative to the state-of-the-art amine technology by half. And it's also lower cost than most other decarbonization pathways, including electrifying certain assets even as low as $30 a megawatt hour for baseload electricity, or hydrogen firing as low as $1 a kilogram. And that is where hydrogen and electrification are options. In industries where you cannot electrify, or it is not easy to electrify or hydrogen fire, like cement and steel, carbon capture is likely to be the best approach, and we cut those costs in half. And it's not just model cases. We actually run our techno-economic modeling through every major asset in the US and show that our approach could be the lowest cost path to decarbonizing all of these assets. That's 1.7 billion tons of CO2 a year across 5,800 sites. So these are sort of lofty claims. Where are we in our journey? We discovered these materials back in 2018 during my PhD work at MIT and went on to build a shoebox-sized system to demonstrate the basic concept. We founded Mantle last year to scale up. We've done a 10,000x jump to a system designed for 0.5 ton of CO2 a day. That's operating in our lab right now. And we have completed the design and started procuring long lead items for a 5 ton a day demonstration project that's going to be sited with a paper mill in Quebec. And we have started designing a 50 ton a day first commercial unit with a global EPC. So from there, we're building systems anywhere from 50 to 5,000 tons a day across all of those industries, as well as every geography. So we were a founding team of 3. We've since grown to 15. I mentioned myself as a PhD and MBA at MIT. Danielle's our COO, runs everything outside of the lab and used to run power plants for NextEra. Sean's another MIT PhD with a lot of molten salt experience. We've grown to include folks with 25 plus years experience. We're supported by Breakthrough Energy through the Fellows Program. The Engine and New Climate Ventures did our seed round. I think I'm at time. So thank you for listening and happy to take questions.
Thank you, Cameron from Mantle.
I have a question for Cameron. Cameron, it's great you can do a shoebox or mega project. What is there a minimum kind of economic mass of a customer where this makes more sense to them than others? And what is the CapEx like for that customer, or do you have other ways to fund a deployment?
Yeah, so our economies of scale are old school process engineering economies of scale. When we increase the size of a system tenfold, the price goes up threefold. And so that motivates us to go to big systems. A minimum viable product or a commercially viable system is about that 50 ton a day system, which is like a 10 megawatt thermal boiler. That's what we're calling a first commercial. That is a give or take $30 million project. And these projects go up to the hundreds of millions of dollars. The goal in the long term is for these assets to be bankable. And we've heard a lot about this in the conference today. There is a tricky, it is tricky to navigate from where we are to where we need to go. But that is what needs to be done. And so we will be doing it.
Great. Thank you.
So question on your unit economics. So in your presentation, you compared it against the alternatives to decarbonization. What does that mean to a dollar price point per ton of carbon?
Great question, Andy. I tend to do the relative because it varies by a lot of different assumptions. And we typically say we're half the cost of the amine technology. And that includes compression, transport, and storage. It does vary by concentration of CO2, et cetera. But just to give you some numbers, we're looking at $30 to $60 a ton for including compression, transport, and storage from most of these point sources. If you just focus on the capture, we're as low as $15 to $25 a ton. Because really what we solve is we eliminate the energy penalty. So these assets are as efficient as they were without carbon capture. And you're really just paying for that CapEx and levelizing that over the lifetime of the asset.
Can you expand on that energy penalty thought? Is that because molten salts are good heat carriers and there's not much sort of loss in that system, or?
Yeah, that's definitely part of it. But the crux of it is Like most carbon capture, point source carbon capture technologies are fundamentally the same. You have some material binds to CO2 in one environment, and then in another environment, you put energy in to drive the CO2 off. Mm-hmm. That desorption consumes lots of energy, whether it's thermal or electrical or whatever you're using. But the insight is that that reaction is reversible. And therefore, while you're consuming energy in the desorption, you're actually generating energy on absorption. That reaction generates lots of heat. When you do carbon capture at a low temperature, all of that heat is generated at low temperatures. And so it's like low-grade heat that's wasted from the system. But if you do this at a high temperature, now you're generating high-grade heat that can be used typically to raise steam and offset the heat required for desorption. You can't use that heat to drive desorption. That sort of breaks the second law of thermodynamics, but you can use that heat in a way that is useful for these sites and drive their energy penalty to very low numbers.
So it makes sense where you've got an industrial heat user in place.
Yeah, it makes sense for heavy industrial applications.
That was pretty much what I was going to get at too, which is it seems like there's another use case for the industrial heat. And so I'm curious about what needs to be true from an infrastructure kind of layout perspective for this to be applicable. We talked about size. Now we're kind of talking about other uses of heat. What's an ideal case? You had some pretty big numbers there about that seem surprisingly large. I'm happy for you, but I'm curious about what's a ideal site location.
Yeah. So the ideal site is somewhere where all of the heat we are regenerating can be used. And that is mostly like chemical, petrochemical, pulp and paper, basically anywhere folks are burning natural gas to raise heat or steam or some kind of process heat. We can integrate into cement and steel, although it's a little more nuanced. Not the worst case, Sophie, but the default case, if there is not a use for that heat, is you run it through a steam cycle and you output electricity. And that is like the back up option, and our economics are still fairly attractive in that case. Obviously it varies with electricity prices, but the ideal site is where you can use the heat as heat.
Right, and that would have to be some kind of continuous system, otherwise you're basically creating a battery, right?
Yeah, it's where people are using heat continuously.
Yeah,
which is most heavy industrial applications. It's like, yeah.
Cool, thanks.
Great, terrific. Thank you, Cameron from Mantle. Thank you. Judges, take a minute to enter your scoring while we wait for Neocarbon to get set up on stage. Hi, Sylvan. You're on mute.
Hello, hello. Can you hear me?
Yes, we can hear you. Perfect. Okay, just a minute. Judges, give me a thumbs up if you're ready to go. Cool, great. The floor is yours.
Super, thank you. So we are Neocarbon, and we capture carbon at scale with cooling towers. So without getting into too much detail about the problem, because I'm sure you're unfortunately all more than familiar with this graph, we have to remove a vast amount of CO2 from our atmosphere today, billions of tons actually by 2050 per year. And because this CO2 that we've been emitting so far is now creating damages to economies, societies in the hundreds of euros per ton as of today. Unfortunately, removing CO2 is very costly and very hard to scale. Last year, the price for 1 ton of technological removal was over 1,000 euros per ton. So obviously not something we can scale to billions of tons. At Neocarbon, we actually found a way to leverage existing infrastructure and specifically waste heat to both reduce the cost and also accelerate the deployment of tech to really new levels. So on the cost side, we can, of course, as mentioned, reduce the OPEX drastically by tapping into underutilized streams, for example, the waste heat, which is one of the main cost driver of operational cost of direct air capture, but also on the CapEx side, by targeting industrial areas. We have, of course, no groundwork to be done, for example, which is a big factor when you try to build plants like our competitors do sometimes in the middle of nowhere where storage sites are available. And we can also have permitting issues that are completely solved by themselves, or, for example, logistics supply chains are also, of course, working much better there. So that combined with our modular proprietary reactor, we can reach 100 euros per ton of CO2 captured by 2030. On top of this, of course, we can be a lot faster by modular and retrofit design, so we don't have to build everything from scratch, which is in itself very important for our innovation because we can iterate and learn much faster than traditional centralized players. This is also, of course, very relevant for the climate crisis itself, which is a bit of a time-sensitive issue at this point, unfortunately. Finally, working with high emitters in the form of heavy industries, we enable them to have a kind of active role into being a part into becoming a net negative industry and net negative society. In terms of market potential, also here I will not get too much into detail because you're very familiar with it. It's a very huge potential. We did a heavy market analysis, and wasted potential globally would give about 5.3 gigatons of capture potential per year, only focusing on the low-grade waste heat, which is of course something that nobody else can use because people are right now paying cooling tower to get rid of it. We already have over a gigaton, and taking only about 1% of this and reaching the megaton scale by 2030, we will be already a 220 million euro company. So where do we stand today? We're a team of about 10 people that have been going on since a year and a half in Berlin, in Germany. And we built our second iteration demonstrator. So you can see a photo here. We are pretty proud of it. It's about 2 by 2 by 1.5 meter and fully autonomous proprietary reactor with a patent that's being filed that actually can be run at customer sites. So this is what actually the next step is for us. We have now signed a couple customer projects where we're going to install those demonstrator end-to-end capture systems where we can actually start the retrofitting and building the IP around this as well. If you're interested in working with us in pilot sites in Germany or Europe, we would love to hear from you, but also from the US for bigger and sites next year, for example. Thank you very much, and we're happy to answer any of your questions if you have.
Great, thank you. Judges, any questions for Neocarbon?
I love that you're repurposing existing infrastructure for a DAC application. I think that's a clever way to preserve some capex. What does it take in terms of like timeline to retrofit one of these assets, and how long would the facility have to be down for shut down its operations?
So obviously this is something that we are still on the theoretical side of things. So I give you our best guess and our best efforts here. But this is obviously something that's extremely relevant for us to optimize because that's a big selling point for the customer, minimal impact on your existing infrastructure and minimum downtime. So we're talking installation of everything kind of separately from the infrastructure that's there, and then just at the final end, the connection. So we're talking a few hours of downtime on the cooling towers, which in itself is not extremely difficult because a lot of cooling towers typically have backup units that can be run only partially of the time, and we can switch between those pretty much. In terms, what was you had a second part of your question, I think, or was it just about downtime?
Just downtime. I was trying to get a sense of sort of the opportunity cost of
I know installation costs, installation time as well. So we estimate that for a typical installation at scale, which would be about 3,000 tons of removal per year, we can basically do this in less than 6 months. So from basically starting the project to connection, which itself then takes only a few hours.
What does the business model or kind of cost share with the CO2 emitters or kind of generators look like, if any? I know you're talking about shifting in the future to a licensing model. Would be helpful to understand how you see that kind of playing out through your first few pilots.
Yeah, perfect. I mean, so in the short term, some of the first units will be more like selling units actually to utilization customers. So let's not get into this. It's a pretty standard business model of like basically B2B. So in the long run, what we have is a licensing model with our global partners. So those 2 customers projects I actually mentioned are such players that could have, they have access to thousands of cooling towers at different sites globally. And they would basically be really willing to take on the kind of manufacturing and operation side of things because they typically also operate cooling towers, which means they already have a kind of manufacturing crew and maintenance crew going on site every few weeks to every few months. And so this is basically what they would add to their portfolio of products and services. In terms of rev share, we would still be doing, for example, carbon credit brokering. So this is a cut of the carbon removal credits we would take. And then, of course, a license fee on the tech. So we are aiming for anywhere between 15 to 25% license revenue, basically. So it's a rev share with those guys.
And what's to prevent them from developing this capability in-house and circumventing y'all?
Well, obviously, none of this works without the strong IP portfolio, which we are developing already right now. So as I very briefly mentioned, the current reactor design, which we have in those demonstrator we're rolling out, is patented or about to be patented before we roll them out in Q1 next year. The patent is basically being filed in the next couple of weeks, so it's really on the final line there. But we also have the next-gen reactor and the larger, let's say, more efficient units coming at the end of next year. Those would also have all sorts of patents around the retrofit aspects and also the reactor design. So, of course, these are things that then when you license it out, of course, some companies will be able to copycat and something like this, but ideally, this is not the kind of partners you would get in cooperation with.
Have you been able to validate like life cycles of your system inside the cooling towers, ability to tolerate contaminants, all of those types of questions that would only really be answered as you get to sort of the industrial scale and industrial applications?
So, I mean, on this front, the short answer is, again, in practice, not really. This is what those customer projects, these pilot projects we are rolling out now will be really helpful to learn. We have, of course, been in contact now. The company is a year and a half old, and I think since the very first few months of the company, we've been reached out by a lot of different cooling tower manufacturers and cooling tower operators. So we have ongoing discussions around all of the challenges and potential kind of solutions around those challenges, but this is still very theoretical. So this is really the next big step for us is kind of when we roll out those pilots in the next few months and actually validate that we can actually run a system. Right now, the demonstrator that we have in our workshop has been completely self-standing and, of course, very controlled environment, TRL 4. So we're moving to TRL 5 now and running this into the real environment. So still at small scale, but real environment at the customer site with the retrofit in place.
I'm not sure if we have time for one more question, Victoria. Are we all wrapped up?
Yeah, very, very quickly.
Are you able to access any Inflation Reduction Act related, 45Q related benefits? I've seen difficulty with that from this distribution approach in the past.
Yeah, so I mean, I'm assuming you are referring to NOIA, one of our companies in the US that used to be doing very similar things, and we always, have no shame mentioning that they were very big inspiration for us in the beginning. Of course, very different technology because they were focusing on the US market, where cooling towers and HVACs in general are very different from what you have in industrial applications in Europe, and of course, the technology itself was very different. So being in Europe for now, we obviously don't have anything related to the IRA. We are, of course, targeting now in the future, let's say next year, as I briefly mentioned, some installation in the US as well, because the US government is so proactive on the DEC field. And we don't expect actually any issues with the IRA because, again, we're focusing more on industrial cooling towers, which can be very, very big. So the average cooling tower can give way above 1,000 tons per year, and even in tens of thousands of tons per year if we talk to like more the heavy industry / power plant kind of cooling towers.
Mm-hmm. Great. That's all the time we have. Thank you, Sylvain from Neocarbon.
Thank you so much for having me. Bye-bye.
Bye. And now we're going to welcome back to the stage Torsten from Carbon Naughton.
Okay, so I share my screen.
Okay.
Oh, cool. So why can't I share? No, I must.
Maybe you can email your deck to Stefan, and Stefan, maybe you can help us drive the screen share. Does that help?
I needed permission from the system. Oh my God.
You definitely do that.
Yeah.
So whatever you're doing before worked, but if you want to shoot me the deck, I can get it going.
Can see me?
No, I think it's best if you just email the deck and drive the screen share for you.
I click on share and it doesn't work. I'm in Chrome. Share screen. Oh man.
Victoria, we have the deck too and the scorecard if you want to drive.
You have the deck?
Stefan, I just pasted the deck in the chat if you want to screen share for us. Awesome. Thank you.
Okay. Oh, this is the this is the long deck.
Okay, the floor is yours.
Oh, the wrong deck. Okay. How can I move the slides? It's not possible. Okay, down. Down. What we are doing down? The next slide. Yes, we take woody biomass. They must be lumpy and sticky. Different kinds, also with problematic waste streams like metals, bones, metals, plastics inside. And then we have our own carbonization technology. We are building up these minus CO2 factories. We also operate them. And within these factories, we have 3 products. These are biocarbons, pyrolysis oils, and the syngas. And the syngas we use for the process to heat the system. And after we produce granules ready to use for the plastic industries, up to 50% filling rate. So the material will improve the properties, and we are much more cheaper than the fossil-based materials. Next slide. You can see some proof of concept. Next slide. Time's running. Next slide. In agriculture, we have a ready-to-use granule for the farmers to generate a Terra Preta effect and a biostimulant, which is also used as a bioseed. Next slide. Next slide. Some proof of concept. Next slide. Okay, in construction, we fill the carbons into concrete, asphalt, screeds, and other insulation materials. So these materials are also carbon dioxide negative. Next slide. Next slide. This is the long version. Down. Sorry. We have huge amount of renewable baseload capable energy. We can offer to third parties 900 degrees by steam or electricity, or we can produce biocoke for steel industry. Here you can see some partners we are working within. Next slide. Next. This is the first impressions of our pilot plant. It's running well. Next slide. These are the products, the oil and the carbons. Our USP is a holistic approach. In the center, we have a patent pending of these materials. Next. We are currently in a financing round of 5 million up to 20 million for the next factories. Next slide. As we're currently planning different, the internationalization, for example, in Slovakia and in China. Next slide. You can see a big deal with China or not. And these are the revenues in the next years. It's a very conservative preview. Next slide.
Okay, I think we're down to the last 45 seconds.
Okay. Next slide. Ready. Okay. We have a good team, engineers, scientists, and producers. And then last slide. The shareholders, we currently raised 6.6 million euros. And last slide, I think. These are the scientists. And then the last slide. This is my motivation, 2 of my 5 children. Thank you very much.
Great. And let's get through the judges, and hopefully we can tease out some details through the Q&A.
Yeah, the pictures imply that you have some partners that have made some products out of the raw materials that you're providing. Are those just mock-ups, or have you had companies do prototypes or not? And to what scale might they go to if you can supply?
So we have a small machinery to produce, for example, the polymer granules. We are in a reception phase, so we get specifications from automotive industry, construction industry, and then we are mixing these or combining these carbon powders. These are very fine powders, 0 micrometers and less, and this is is an IP, and then we mix it up to 50% currently. So we avoid these other 50% fossil-based or bio-based polymers. And with this combination, we have a very low price, up to 40% less than the fossil-based. And this is very interesting for a lot of companies we are working on, because at the end of the day, it's not sustainability we talk about, it's the price. And so we are very attractive, and we can, with such compounders in the big factories, for example, now in China we are planning with 20 modules, we are producing more than 30,000 tons of biocarbons, and so we can imagine up to 100,000 tons of these polymer, or also in construction. These are first prototypes and pre-industrial processes, but it pretty works well.
Thank you.
Thank you. I think I mostly agree with the sentiment of your shirt here, but I would love to understand maybe just a little bit more about the technology. If I understood it right, are you taking biomass and then doing like a pyrolysis to it, producing both a pie oil and a biochar?
Yeah, and there are other technologies doing the same, nearly the same, but we have a big difference because we have a batch retort system. It's a very robust system. We have no turning parts inside, so we can process every kind of booty and lumpy biomass with metals inside bones. We don't must prepare it because preparation by biomass is very expensive. The second is during the process we can control the temperatures to earn these high quality oils by a very low temperature, 400 degrees. And then we can increase the temperature for a high quality of biocarbons. So this is a very flexible system. And by the output, you must understand that the other technologies also are always flash pyrolysis systems. So they have roughly 20 minutes in the oven, and then you must cool them down with water. But when you have water inside the carbon, it's not useful for the polymer industry. And we use our own syngas to cool it down within 3 hours, these batches, and then we have 100% dry biocarbons. And our hidden champion is the pyrolysis oil, because the pyrolysis oil is like a fossil-based oil. You can produce pharmaceuticals, you can produce polymers, you can produce biobitumen. This is a black gold for us. So this is a big difference, and also the dimensions. We're talking about factories starting from 10,000 tons of biocarbons at least, up to 100,000 tons. For example, for steel industry.
The elimination of the feedstock prep is a big deal. It's a big cost point in a lot of bioprocesses. What does the consistency of the product look like out of this system? And does it vary with the feedstock you're putting in?
Because, sorry, about the question?
The product, is the product consistent that comes out of the system, or does it vary a lot with your feedstock?
Depending on the feedstock, we have different qualities in the biocarbon, so we can produce blends because we have a database, a biocarbon database, and then we can produce these blends we need to deliver standard quality to the industry. Because when you talk with the big industry, they always need a standard quality at least. And so it's possible that we mix different kinds of feedstocks for one plant to produce, for example, these granules.
Running with the feedstock line of questioning, tell us about where that's coming from. Seems like a classic case with feedstock is what are you competing against? How are you able to pay a higher price? And then the secondary carbon and climate implications of that, of what's the alternative?
About the feedstock? So, so the feedstock is very different. We can use waste wood, we can use wood chips, screen overflows, different kinds of feedstock. And so the price by the input is not very important because our value chain is so deep that we can influence the price of the end product and in correlation to the input. So when the price of the input material is increased up to maybe 20 or 30%, this has an impact on the end product.
Okay, great. Great, thank you so much, Torsten from Carbonauten. Again, I want to recognize the teams that presented today: Carbix, Carbonauten, Sequestrate, Mantle, and Neocarbon. And for everybody who's watching, reach out to them and network and find out about how they're moving innovations to address carbon issues. So come back to the main stage tomorrow at 11:05 Pacific, where we're going to announce the winner and also get feedback from the judges. So thank you so much for joining the session, and enjoy the rest of the conference. Thank you so much. And the judges, I'll see you on the Zoom link.